In this lab, we measure the half-life of radioactive indium and simulate radioactivity using both coins and dice. If one begins with N0 radioactive nuclei at time t equals 0, then after a single half-life there will be N0 over 2 nuclei remaining. After 2 half-lives, 1/4 of the nuclei remain, and after 3 half-lives there will be only 1/8 of the original number of radioactive nuclei left. This decay of nuclei may be expressed as capital N, the number of radioactive nuclei remaining after little n number of half-lives, equals N0, the original number in the sample, times 1/2 multiplied by itself, little n times. At any intermediate time, t, we will have N0 times 1/2 raised to the ratio t over t 1/2. Thus, given the half-life, we can predict the number of radioactive nuclei remaining after time t. The activity is what we will actually measure using a Geiger counter. Activity is defined as the rate of decay, delta n over delta t, in counts per second. Now it so happens that the rate of decay is proportional to the number of radioactive nuclei present in the sample, with the constant of proportionality being the decay constant, lambda. The negative in the proportion just indicates that the numbers are dwindling rather than growing. If the likelihood of a given nucleus decaying in a given second is small, then lambda represents the probability of that nucleus undergoing a decay each second. The decay constant lambda enables us to use the exponential function as we did in the case of the discharging capacitor. Instead of 1/2 raised to some power, we have e, the base of the natural logarithm, raised to the negative of lambda times time. Since the activity or count rate is proportional to n, the activity decreases with the same exponential decay curve and having the same decay constant. One can make the connection between half-life and decay constant by setting the ratio of n over n0 equal to 1/2 when the time t is the half-life. Then 1/2 equals e raised to the minus lambda t 1/2. Taking the log of both sides gives log of 1/2 equals minus lambda t 1/2. The negative of the log of 1/2 is just the log of 2. So the half-life equals log 2 divided by lambda. Thus, measuring lambda yields the half-life. Experimentally, we begin by activating the sample by placing it next to a strong source of neutrons inside a container shielded by water. The sample is placed between layers of paraffin to slow the neutrons. We slide the sample toward the source and raise the source so the sample is no longer shielded by the water. Placing the non-radioactive indium, mass number 115, next to the neutron source, we can embed a neutron to transform it into the unstable isotope indium 116. We now reverse the procedure to remove the radioactive sample of indium 116. The unstable isotope of indium will decay into tin with the emission of a beta particle. The half-life for this decay process is about 54 minutes. Your goal is to monitor counts with the Geiger counter to measure this half-life. In Data Studio, set the sample rate to 1 minute and the stop time to 3600 seconds, or 1 hour. The Geiger counter is set to record counts for 1-minute intervals and store and plot the results for 1 hour. Place the sample under the Geiger counter holder and hit the Start button for collecting data. For the next hour, do not disturb the sample or detector. You don't want to alter the distance between source and detector. After 1 hour, you will have a plot of activity, counts per minute, versus time. Transfer the data to graphical analysis and fit a function a times 0.5 raised to the b times x. The half-life is the inverse of b. Note that we have added error bars. The errors involved in a sampling process of this nature are expected to be equal to the square root of the total number present in the sample. If 100 counts are made, then we expect an error of plus or minus 10. If 10,000 counts are made, then the error is plus or minus 100. We can also fit an exponential function to determine the decay constant. This time we fit the function a times e to the cx, where c is the negative of lambda. A plot of log n, or log count rate, versus time will yield a straight line with a slope of minus lambda. While you are waiting for the Geiger counter to complete its 1 hour of work, you can perform a simulation with coins and dice. Start with 100 coins, flip all the coins at once, and separate out the heads from the tails. Keep track of the number of tails remaining. Collect up all the remaining tails, shake them vigorously to reset them, and flip them over again. Proceed in this way until there are few tailed coins remaining. Record the number of coins remaining for each trial number, including 100 coins when the trial number is 0. Plot the number of coins remaining versus the trial number. Adding results from all groups will reduce the relative error considerably. Instead of flipping 100 coins, you will have data on nearly 1,000 coins, depending on the number of groups. Fit a function of the form a times 0.5 raised to the b times x. The inverse of b is the half-life. Now fit an exponential curve to the same data. From this fit you can determine lambda, the decay constant. For flipping coins, the probability of any single coin coming up heads is 1/2. Thus 1/2 equals e to the minus lambda times one single toss. Taking the log of both sides gives the decay constant for the coins equal to the log of 2. The half-life is thus log 2 over log 2, or 1 toss. 1 toss is enough to remove approximately 1/2 of the coins in the sample. Makes sense. Finally, plot the natural log of the numbers of coins versus trial number. The slope of the straight line should be lambda, that is, the log of 2. For the dice, we remove all the dice that come up with a single dot. Determine how many are left and roll those dice. Repeat until only a few dice are left. Again, add the results from all groups. Record the number of remaining dice versus trial number. Plot the number of dice versus trial number and fit 0.5 raised to the b times x to get the half-life from the inverse of b. Fit an exponential to the same data to get the decay constant. Finally, plot the natural log of the number of dice versus the trial number and get the decay constant from the slope of the linear fit. Since all the die have 6 sides, n over n0 is equal to 5/6 when t equals 1 roll of the dice. Taking the log of both sides gives a lambda of log of 6/5. The half-life should thus be log 2 divided by log 6/5, or approximately 3.8 rolls. In approximately 3.8 rolls of all the dice, we will expect to have removed about half of the dice.